Hello, everyone, and welcome back to the Maverick Statistics channel. This is Jeff Mankowski, and in our last video, we saw an introduction to the range, the variance, and the standard deviation. And what we're going to do in this video is do an actual example of computing the standard deviation. And it's going to turn out that we need to compute the variance to get to the standard deviation, so we're going to learn how to do both in one shot. So what we'll do is we'll bring a data set up on the screen to work with. And before we get into the computations, we're going to take just a couple minutes to talk about conceptually what the standard deviation is trying to do, what it's trying to measure, so that way the computations are a little more meaningful to us. And let's go right ahead and let's bring up a data set on the screen here. And this is one of the same two data sets that was used in the last video. It's actually data set A, so it represents the drying times of a sample of paint from one particular brand. So for example, somebody used this paint brand, and in one instance, it looks like they might have painted a room, and it took 4 hours for the paint to dry. In another instance, they painted a room, and it took 6 hours for the paint to dry, and so on and so forth. Now, when we do the standard deviation, remember, one of the big selling points of it is that it takes into consideration the location of every single value or observation in the data set. And what it's going to do, in principle, is it's going to find the centerpiece of the data set, the mathematical average, which would be, for us, the 10. And it's going to look at each observation and kind of gauge what the distance between that observation and the mean is. So, for example, it's going to look and say, okay, we've got a 12 in here. How far is the 12 from the mean? We've got a 14. How far is the 14 from the mean? It's going to do the same thing with all the numbers on the left side and on the right side. And once it's gotten all these distances, it's more or less going to go and compute what's the average distance between each value and the mean. So now that we know that, before we get into the computations, let's go and write a few important takeaways here. We're going to go ahead and undo this, and let's write in a text box here. And we're going to say, basically, the standard deviation is trying to determine the average distance Okay, so if we know that, let's just take a minute and think about what happens if the standard deviation goes up or the standard deviation goes down. What does that mean insofar as what's actually happening inside of our data set? So 2 more takeaways let's put in here. Right down here, we're going to come in and say, and let's use red, why not? If the standard deviation were to increase, that must mean that the average distance between any given observation and the mean is going up. Okay, so if that's what's happening, that means that if we look at the data set's starting to spread out. In the last video, we were talking about how the standard deviation can measure dispersion, and this is kind of saying if we look at our data set, if we were to find the mean, which is a 10, what it's trying to say is all the values would be starting to pull away further from the mean. So if we found out the standard deviation was increasing, it means the data set values, the observations are getting further and further spread apart. Okay, so if we know that's what happens when the standard deviation increases, then what happens when it goes down? Should be the opposite effect, right? So let's go ahead and let's put in another text box here, and we're going to say, let's get this written in. If the standard deviation this time decreases, okay, now if that happens, the data set must be getting more compact. So the values are getting closer to the mean. Let's go ahead and open up our box. And we're going to say observations. All the observations would be moving closer to the mean. So in this case, if that's what's happening, here's our mean. The implication is that the values are all kind of gravitating closer towards the 10, like that. So remember, think of that standard deviation as like an accordion or a set of curtains that's getting more spread out, or it's getting more crunched up, and it's telling you that that's what the observations are starting to do as that standard deviation goes up and down. So now that we know this great stuff, let's start to move into our computations. We're going to get rid of some of these takeaways here, get some room. Okay, so if we know we're measuring the distance between any given value and the mean, it would probably be a good idea to start just by making a list of our x values. So we're going to go ahead to prepare. We're going to list all of our x values from start to finish right down here. So we're going to say we got a 4, a 6, an 8, a 10, 12, 14, and a 16. Now we're going to get ready to start taking each of those values and subtracting it from the mean. So we're going to put in another column here. We're going to say x minus x bar. And remember, in statistics, x bar is our symbol for the average of a sample. So row by row, we're going to do our subtraction. 4 minus 10 would be a negative 6. 6 minus 10, 4. We're going to fill in all these values. Okay. Now remember, our goal when we started was we wanted to go and get the average distance each value was from the mean. So according to that, we'd have to take this whole bunch of numbers and compute the average, add them up and divide by the total. Now what's going to happen if we do that, if we try to add the negative 6 with the 6, the negative 4 with the 4, we're pretty much going to get zilch because all the numbers would cancel out. It leaves us with 0, and we can't really take 0 and divide it by anything. And that means that we have to do something to get rid of the negative sign so we don't get this massive cancel out effect. And what can we do to get rid of the negative signs? Well, there's lots of stuff. There's absolute value. We can multiply by -1. We can start squaring things. And for us, what we're going to do is we're going to start to square. And there's a certain reason why we're squaring terms. We'll find that out a little bit later. It's kind of an advantage that we get. So what we're going to do is put another column in right over here. We're going to write down the exact same column we had before. So we'll put in x minus x bar. The exact same thing, except this time we're taking each of those numbers one by one, and we're going to be squaring them. So we're going to go row by row, top to bottom, take all the squares of everything in the preceding column. Negative 6 squared will be a 36. This one's going to be a 16. We'll have a 4, a 0, a 4, a 16, and a 36, just like so. Now, if we wanted to go and compute the average of all these values, could we do it? Would we have anything stopping us when we tried to add everything up? And we'd say, absolutely not. We can come in, we can add all these up, and we would find out that we'd end up with a 112. Perfect. So let's take this 112, let's pull it all the way up to the top, and we're going to say we've got our 112. And intuitively, we'd come in and we'd say, well, if we want to get the average distance there, we would divide by the total. And we're almost exactly correct. We had 7 numbers. What we're actually going to do is divide by 1 less than the total number of observations, which would be 7 minus 1. And in the next video, we'll explain why we're subtracting 1. First, just to finish this out, if we took 112, we divided it by 7 minus 1, we're going to end up with 18.6. Now, before we interpret the 18.6 and talk about exactly what that means, let's just summarize everything we've done, because we've built in a lot of columns here. We want to get a good handle on this. Now, remember, to start with, what we had to do was ultimately we took each value and we subtracted it from the mean. So let's go ahead and say on the numerator here, to get to the 112, the first thing we had to do was take each value and we subtracted it by x bar. Now, once we did that, the next thing we had to do, row by row, was we had to square all those values, didn't we? So what we're going to do, let's write down, we've got, let's keep things in the same color here for just a minute. Okay, we've got this squaring value right here, and we're going to say at the end, we came around and we squared everything, just like so. Okay, so once we did the squaring stuff, what happened next? Well, at the very end, we had all these squares. We had to come in and we had to add them up, didn't we? And in statistics, we use a summation sign on the outside to indicate that we've added something. And on the bottom of our formula, we had 7 minus 1. And that 7 stands for something. It stands for the total number of observations. And in statistics, we symbolize that with a lowercase n. So we're going to write in lowercase n. And of course, we also did subtract 1. We still don't know why, but that's coming. And we're going to go ahead and box up our formula. And we'd say, okay, this is great. We calculated the standard deviation and we figured out the formula. Almost. What we actually did was we just calculated the variance of our sample. So to calculate the variance and then get to the standard deviation is just one more step. But first, let's just write in a little piece of information here on the side. We're going to say we computed the variance. And that's the variance of a sample. And you might be wondering, well, gee, do we have a symbol so we don't have to keep writing out variance of sample? And absolutely we do. We're going to call this S squared. Okay, now that we've got that all taken care of, we're going to kind of walk back and say, when we got to this 18.6 right here, what did that 18.6 really stand for? And according to our computations, what we figured out was what's the average square distance between each observation and the mean. And that's all well and good, but remember when we started out, we just wanted the average distance between each value and the mean. We didn't want to do all this squaring stuff, so it's a little bit awkward for us. And think of it like this. If you drive 4 miles to get to your job every day and somebody says, how far do you commute? You wouldn't really say, I drive 16 square miles or 16 miles squared. People would look at you and say, well, just tell me how far you drive. So we need to do something to reverse the squaring so we get this back into the practical context of the exercise at hand. So in mathematics, what undoes squaring? And we'd say, I know what to do. A square root would reverse a square. So what we're going to come in and do is down at the very bottom, we're going to take 18.6 and we're going to put it under a square root sign. And when we compute the square root of 18.6, we're going to get 4.32. We're going to write that in. Mathematically, to show what we just did, we took the formula that we had just boxed up and we basically put that thing under a square root sign. So let's go and say our formula is going to be the same thing we just had up at the top, x minus x bar. Let's get in our square, and at the bottom, n minus 1. And we're going to box this up together too. And this is going to give us our standard deviation. So we're going to go and put standard deviation. And we'll write in of a sample. Okay. Now, if the top side we called S squared, what's our guess of what the abbreviation is going to be for the bottom here? And if you guessed, well, it's probably just an S. You're absolutely correct. So now that we've got all this great stuff together, let's take just a moment and let's really interpret what this 4.32 means. The 4.32 is basically the average distance between any given value and the mean. So in a practical context, what it's trying to say is, imagine we look at the back of the can of paint. The manufacturer writes in that this can of paint is going to dry within 10 hours. Now, we know that when we have an average, guys, we've got kind of a little bit of fluctuation around the average. There's going to be some give or take. And we kind of naturally want to know, well, how much give or take is around the mathematical average? That's exactly what the 4.32 is trying to tell us. It means that if we look at the can of paint, we see the average of 10. We use that can of paint, we paint a room, and we're probably going to dry within about 4.32 hours of the mean. That's what the standard deviation is trying to tell us. Now, how is that helpful? Well, in the practical context of what we're talking about, if you want to make sure that your product is very, very reliable, do we want a standard deviation to be very high or very low? And the answer is we want that standard deviation to be pretty low most of the time, because if it's low, it means that what's going to happen in reality will be closer to the specifications that are specified by the manufacturer. Like, is that 4.32, if it were to get smaller and smaller and smaller, it means the likelihood is getting larger that when we use the paint, it's going to conform to exactly what the manufacturer said in terms of drying time. So think of it as the closer the standard deviation gets to 0, from a quality perspective, better off the product is going to be. So in the next video, we're going to talk about a few more key takeaways between the standard deviation and the variance, and I'll see you on the next video.